So yes, I'm going to present you this paper, which is on archive, which is called Quantum Bounds for Compiled XOR Games and the Outcome CHSH Games, which I did in collaboration with mostly people in Paris and, well, my supervisors, of course. So, wait a second. Okay, now it's working again. What are we going to do? We're going to first define this compilation procedure. So I'm going to define to you what I mean for compiled games. This compilation procedure, it's a general compiler that maps Bell nonlocal games to some other classes of games in which we try to remove the space-like separation between the parties. This is kind of the very general idea. And I will try to convince you why this is useful, why this is important. For this kind of compilation procedure, the people that proposed it were already able to prove a separation between classical and quantum. So it's already working as a proof of quantum advantage. But they couldn't really characterize very well the quantum strategies in this new set of games, in these compiled games. So this is actually what we're going to do. And I'm also going to present you our results. So we didn't manage to yet characterize completely the quantum strategies in these compiled games, but we did manage to have some results for some partial sets, some partial classes of games. So let's first set the notation so that we are all on the same page. And let's first define Bell non-locality. Well, I guess all of you know very well Bell non-locality. Bell non-locality is based on games in which we have separated players, spatially separated players that are receiving some inputs from a central node that we call the verifier. So this verifier will sample some questions, will send them to Alice and Bob that are not allowed to communicate anymore when they receive the inputs. Then they can operate however they want on these classical inputs, and they will commit some classical outputs, A and B, to this central verifier. Then we will repeat this procedure many times, and the verifier will be able to evaluate the behaviors of this game, the correlations, which is simply the probability of having some outputs given some inputs. This is kind of the very basic structure of Bell non-locality and all of non-local games. The idea is that this is the simplest framework in which we can show a separation between classical and quantum behaviors. Which means that we can define some linear combinations of these guys, of these correlations over here, choosing some coefficients here, for which we have that the maximal strategy, the maximal classical strategies is achieving a bound which is strictly less than the maximal quantum strategy, which means that if we achieve a value which is here in between, we are sure that we have to use some quantum resources involved in the games. Why is this? Well, in these non-local games, it's pretty easy to see that, for example, one thing that quantum players and classical players cannot do is to share some entangled resources. So if they share some entangled resources, of course, it's going to be easy to tailor some task by choosing some appropriate coefficients here, in which quantum provers will outperform classical provers. So I also want to fix the Bell operator formalism, which is kind of the most common formalism used to describe non-local games. What we usually do is that we define this, which is a Bell operator. We model the two provers, two or more, but let's fix the two for now. We model the two provers to live in two different Hilbert spaces. So we can describe the general state as the tensor product of these two Hilbert spaces. And then all of the strategies that Alice can apply and that Bob can apply can be represented with observables. Then we can build this, which is just a Bell operator. And to have the Bell score, the equivalent of this guy over here, we just need to project this Bell operator on a shared state. Again, if this shared state is entangled, this is producing correlations that a classical local hidden variable model couldn't replicate. Okay, so let's fix the concept even a bit more with the CHSH game, the CHSH inequality, which is the very first one, the very basic one that everybody knows. So what do I mean for fixing a game? It's really just to fix this Bell operator, so the coefficients of these strategies. And it is very well known, it is very well proven, both theoretically and experimentally, that a classical prover, two classical provers can reach this bound, can only reach 2 using the best optimal strategy, but a quantum prover can reach a bound which is slightly higher. And here I represented the CHSH polytope. So here you have to think of this image where every point it's collection of correlations. And we know that classical correlation is a polytope which is included in a bigger set, which is a convex set, which is representing all quantum strategies. And these quantum strategies are included in an even bigger polytope, which is the non-signaling properties. And it's very nice, this graphical representation, because it makes it really clear that there are some bounds in this picture, but inequalities would be just some lines that are separating the sets. And it's clear that there are some bounds, some correlations that quantum can achieve and classical cannot. Another very nice property that we are much interested in for example, CHSH and in general non-local games is self-testing. So what does self-testing mean? Self-testing means that for some inequalities, we can prove that when we saturate the bound, when we saturate the quantum bound, which we call the Thierson bound, we can prove that there is a unique quantum strategy that can achieve that bound. This is super powerful because it's a very powerful way of certifying quantum resources, which is in general is a very difficult task. So yeah, for example, for CHSH, we know that if we saturate this bound, 2 square root over 2, we know that the 2 local provers have to share maximally entangled APR pair and have to perform measurements that are of this shape, anti-commuting, and exactly on this shape. Of course, we can only define self-testing up to global unitaries and additional degrees of freedom that we cannot self-test. So this is kind of the motivation that, like our starting motivation was, okay, this self-testing procedure in particular, it's very much related to a lot of very, very useful protocols that are used everywhere in quantum information theory, verification of computation, verification of quantum resources, and all of that. The problem is that we can be sure that this is true if and only if we can be sure that the two spatial parties, the two parties playing the local game are absolutely not communicating, are not able to share any information about their partial information of the game. Doing that, it's a very heavy constraint, and usually experimentally what we try to do is that we really try to put the two players like distant enough such that we are sure that they couldn't communicate. If we put them in 2 different icons, of course they cannot communicate because of the laws of physics. So what people started to try to think is what happens, like how can we start to try to remove this space-like separation constraint? Can we try to conceive an experiment in which we still have all of the nice property of non-locality, all of the nice property of certification coming from self-testing, but without having to impose that these two parties, Alice and Bob, are absolutely forbidden to communicate, which is something that it's very difficult to check in principle. So the idea is to not consider Alice and Bob separated anymore, but put them in one single block that I will refer to as a single prover that is communicating with this verifier, and from which, of course, we cannot hide information. So if we try to do it in a very trivial way, if we just try to send all of the inputs on the clear to a single prover, then this game is clearly not going to preserve the difference between classical and quantum strategies, right? So we all know that CHSH game, the difficulty of winning the game with a quantum strategies is not much in trying to evaluate a difficult predicate, but it's more of coming from like the difficulty, it's coming from the fact that the parties have partial information, that they don't know what the other parts received. So of course, if we remove spatial separation in this way, and we just give both input to a single prover, this kind of difficulty is completely erased, and this kind of game, even a classical prover can achieve any correlation. Any classical prover can achieve any behavior very easily here. So this is clearly not interesting. So what is the idea that people had? Well, we want to try to hide partially the information from a single prover. Let's use cryptography. So let's use cryptography to simulate the spatial separation and to hide partially the information from the single prover. So an idea would be to use this, so to send encrypted inputs to the single prover that then could evaluate encrypted outputs and send that back to the prover. Why this single prover, how this single prover can correctly evaluate the encrypted output? Well, this comes from some results that are known in classical encryption, and they were extended to quantum encryption, which is using this framework, this functionality, which is homomorphic encryption schemes. Homomorphic encryption, the very basic idea is that it's allowing us to compute some circuits on encrypted data without having to decrypt them, okay? So using quantum encryption schemes, we can perfectly reproduce all of the behaviors that we were having in the non-local games before here. Yes?
So the encryption will allow you to compute the logical end of X and Y, right? Rather than the encryption of the logical end of X and Y.
Sorry, can you repeat again?
So what you want to do for CHSH, if you would like to know what is the logical end of X and Y,
Exactly.
and then find A and B whose parity equals that logical end.
Yeah, well, okay, but no, so the encryption is not going to allow to compute the encryption. Okay, well, in this situation, yes, but we want to prevent it in general because we would like this quantum prover to have the same power of the two separated, spatially separated non-local prover.
But you're not there yet.
Exactly.
Okay.
So this is exactly the point. So this prover, the point that I wanted to do here is that this prover using homomorphic encryption, it's going to be powerful enough to reproduce all of the correlations of the non-local spatial separated counterparty. But the problem is that this is too powerful. Exactly, you are completely right. So here it has been proven that a classical computationally bounded single prover is able to reach the non-signaling bound of CHSH, for example. So this prover is too powerful. It's not preserving, again, the difference between classical, like the gap between classical and quantum provers. So the protocol that we are now going to study, it somehow seems to, it's proven to preserve this quantum advantage. So yeah, this protocol was proposed by Kalai and collaborators a few years ago. It's actually very recent. It was published in 2023. And the very basic idea that they had is that we also need to enforce some very precise time ordering to preserve the difference between classical and quantum. So first, we're going to compile any two non-local prover games to a single prover in which the first part of the single prover is going to kind of mimic the behavior of Alice. So we first send the encryption of the first input. We wait for the single prover to commit back the encryption, the encrypted output. And then only at this stage, we can simulate what Bob is doing, and we can send him the Y and wait for the B. We don't even have to encrypt this second round, because if the encryption scheme is secure, then the single prover cannot have any knowledge about X and A. Okay? So to be a bit more precise, what they use here for the encryption, so they really develop their protocol using this quantum fully homomorphic encryption scheme, for which we have to impose two conditions. The first condition that we ask is correctness with auxiliary inputs. These conditions are a bit technical, so I just really want to sketch to give you the idea of why they're doing it. So this first condition is necessary to ensure that the encryption scheme is well behaving with entanglement. So the idea is that here, if we think of the single prover producing an APR pair and keeping the first part of the APR pair for the first part of the protocol and giving the second part to the second part of the protocol, then we're going to act on the first part of this APR pair with some homomorphic encryption circuit. And this condition here, it's ensuring us that the other part of the entangled pair, it's going to behave correctly with respect to the circuit that is happening in the first part. And then the second thing that we ask for is in CPA security. So I don't know if many of you have this crypto background. The idea of in CPA security is that we need to bound this single prover not to be able to distinguish the encrypted inputs with a probability which is higher than random guessing. It means that here, after we played the first part of the protocol, whatever Bob is trying to do here, Bob can only do a computationally bounded operation on what's happening on the state that it's left from the operations of the first part of the protocol. And this operation, I just define it as a general observable here. And this general observable cannot distinguish between two different distributions, D0 or D1, with a probability that is higher than a negligible function in the security parameter. Okay, so this is not precisely the in-CPA security statement, but it's, let's say, the adapted version for this kind of game. And yeah, this is just notation. So yes, we usually just use these curly approx to say that these two quantities are negligibly close. Okay, so
Any protocol satisfying those two conditions?
Yes, there are protocols. So exactly, the reason why they fix it is because there's a protocol by Mahadev of 2018 that is indeed satisfying. Actually, they are very reasonable conditions for a quantum homomorphic encryption scheme. They're nothing crazy. So what they can prove in the original paper, which they proposed this compiler, is that for a computationally bounded single prover, we have classical soundness, meaning that a classical prover, which is bounded, it's going to be able to do all of the correlations that the non-local classical provers could do and cannot do more. So we are sure that the bound is preserved. Here, used again the CHSH polytope to kind of represent it graphically. We know that the classical prover cannot perform better than this. And they can prove quantum completeness. So they can prove that with this quantum fully homomorphic encryption scheme, the single prover can do at least as good as the quantum non-local provers, okay? So this is good enough for them because this is already a proof of quantum advantage, right? We already proven that there's a classical bound which is here and that we can for sure achieve a quantum bound which is higher. But what they couldn't do is that they couldn't prove the soundness of the quantum bound. They couldn't characterize if this new quantum prover it's more powerful, less powerful. I mean, not less powerful. They proved that it's at least as powerful, but they couldn't prove how fast can it go, how bigger can it go. So yeah, in principle, it could have in principle, we could even reach much weirder correlations. We could reach the non-signaling bound. We don't know. So yes, many people, us as well, we started trying to dive a bit deeper into this, try to model the quantum strategies that are possible to achieve from these computationally bounded quantum single provers. So we simply model the first part of the protocol by operating with some observable with encrypted input and output, because again, the single prover cannot decrypt this. Then we can think of this first part of the protocol as acting on a general state, which could be entangled with some other register, we don't know, and producing some general state, which is going to be transmitted to the second part of the protocol, because everything here is in communication. And then Bob is just going to, the new Bob in this single prover is just going to do his measurement with decrypted input and output. And what this single prover is going to have are these encrypted correlations. You see here, there's encrypted A and X. And then from these encrypted correlations that the verifier is collecting, only the verifier can build the decrypted correlation, because only the verifier can know how to correctly decrypt back the encrypted A and encrypted X.
Yeah. So this state C file now, it's not living in the tensor product of the...
Well, exactly. I mean, the general idea is that it doesn't really make a sense here to define a tensor product Hilbert space, right? Exactly. It's kind of up to us, but it makes much more sense to just define a bigger Hilbert space in which maybe this psi is going to have different registers in which can encode different informations. But yeah, we don't need the tensor product structure anymore. It doesn't really make sense anymore. So what people could do last year is to prove the soundness of the quantum bound of CHSH. So people did prove that for the very specific case of CHSH, the quantum computationally bounded single prover cannot outperform the Tierson bound up to a negligible function in the security parameter. Again, so CHSH, it's the thing that I defined to you before, where all inputs and outputs are just bits. And for CHSH, we know a lot of partial results. So they use these two techniques, macroscopic locality and crypto-SS decomposition. So the macroscopic locality technique that they propose is very interesting. What they do is that they assume, okay, let's assume that this single prover is winning this game with a probability which is Tierson bound, so 2 square root over 2, plus some non-negligible epsilon. Then what they do is that they prove that this implies that there exists here a measurement that we could do in the second part of the protocol, which is breaking the security of the scheme with a probability which is linearly going with epsilon, which by definition we said it was not negligible. So they kind of connect the non-negligibility of going higher than the Tierson bound and the difficulty of breaking the INCPA scheme. They prove that if you outperform the game, the quantum value of the game here, then it must mean that you can also break the encryption scheme, which we assume secure by definition. So this kind of way of thinking was very nice, and we actually worked a lot in trying to extend it a bit. The problem is that they really build this operator that Bob has to do in a way which is very specific to CHSH. So it seems very difficult in general to build such an operation, such an observable that could work for any Bell inequality. It seems like you really could take very specific cases, but it cannot be extended to a very general framework. So the other thing that they propose is this cryptographic SOS decomposition, which seems much easier to generalize to broader classes of games. So that's what we did. We tried to extend this second technique that they presented. So first, I need to define to you what is a SOS decomposition. So SOS decomposition, oh, I just noticed that here. Good. SOS decomposition, it's a tool which is very much used in Bell nonlocality, which consists on taking the Bell operator and finding a set of polynomials of degree n in the observable of Alice and Bob, such that we can write something like this. So SOS stands for sum of squares. We basically want to find a decomposition as a sum of squares of this Bell operator, where alpha is a generic constant, which is going to be an upper bound of the Tierson bound, of the quantum bound. Why is it that? It's fairly easy to see. We just need to take the expectation value of this whole expression. Then we know that here we're going to have alpha minus the value of the Bell inequality, which is going to be equal to the expectation value of this guy. But the expectation value of this part, it's positive by definition, because it's the expectation value of a sum of squares of polynomials, which means that alpha is indeed an upper bound of quantum strategies, right? And then if we can find a good decomposition of polynomials for alpha being exactly the Tierson bound, this is very interesting because we prove that the bound is tight. We prove that we can prove that there is a quantum strategy which is indeed saturating that bound. And not only that, this is also very much used in self-testing, because then when we reach this quantum bound, we know that the polynomial have to be the nullifier of the optimal state here. And this is sometimes enough to completely characterize the optimal quantum strategy. It's not always the case, but a lot of the self-testing that we can do in the non-local setting are actually done like using these SOS decompositions. So what is the idea? The idea is that we want to completely borrow all of this machinery which was already developed for non-local games, and we want to map it to work also in the setting of the one single prover case. So we take exactly the same SOS decomposition, and now we define a pseudo expectation value, which is going to retain the important constraints. Yes.
What's Q?
What is Q?
Yeah.
Here. For me, beta Q is just the Tierson bound, the quantum bound. So the general idea of SOS decomposition is that usually people have a sense of what is the Tierson bound already, and then to prove that indeed it's a tight bound and to prove the self-testing, a posteriori you find the polynomials that saturate it. So in principle, you could also take a beta Q which is much higher, and I guess it's going to be fairly easy to find polynomials that decompose it for like a bound which is much higher, but it is difficult to prove it for specifically the Tierson bound. So yeah, this third expectation value map is going to preserve the important characteristic of the expectation of before. So it's going to map identity to 1. It's going to map the Bell operator to the compiled value of the game. So the winning probability of the compiled game, of the single prover game. And ideally, if we can prove that this is also preserving this positivity, then we're done, right? Because then we can prove that the compiled value of the game is bounded by the quantum value of the non-local game. So what is this pseudo expectation map doing? It's mapping correlation from the non-local setting to this one single prover setting, right? So I want this pseudo expectation map to behave like this, but I also want it to do this kind of mapping, to map every polynomial in Alice and Bob observable to something which makes sense in the single prover game. Again, as the remark that you were saying before, here we have something which is living in a tensor product of Hilbert spaces, observables that are acting on Alice and Bob. And here we don't have this tensor product Hilbert space anymore. So, well, if you really want to understand how we did it, I would suggest you to read the paper because it's very hard to kind of really motivate it. So we just really try to sketch it, to sketch the very basic idea. So the idea is that, again, we want to mimic what this expectation value of taking the bracket of a state was doing before. The bracket here, we know that taking the bracket of this tensor product of two observable, it can be mapped to a correlation picture, right? This is just really opening the definition of the observable for binary observables. Then, of course, this is also extendable to higher dimensional observables. So basically, the idea is like, okay, we want this correlation. We don't want this correlation here anymore. We wanted the encrypted version of this correlation that was coming from the game, where we don't have A and X, but we have encrypted A and encrypted X. So this is exactly what we do. We just do a change of variable such that it makes sense in the compiled game. And yeah, and this is how we define the expectation. This is how we define the action of this expectation value on products of A and B. Also, what we do, what I wanted to underline is that here we just do a proposal for this expectation. We just propose one example, which is working for some specific set of games. So what we could do is we could just define the behavior of this expectation value on degree 2 polynomials in Alice and Bob observables. I'm going to motivate it after that. This is still enough to describe some set of games, but this is not a general result. This is not a bijection. This is not the only way in which we do it. So yeah, the other thing that we need to define, since I want this expectation map to work on every degree 2 polynomials in Alice and Bob observable, I also have to define how it behaves on true Bob observable and on true Alice observable. And this is kind of the bottleneck. The problem is that we don't really know how to map this in a meaningful way in the compiled game. So, well, as for now, you have to trust me, and we're just going to take the delta x prime of these two Alice observables, and now you will see why. So basically, we just consider the games for which this pseudo expectation map is good enough to characterize all possible strategies. So we just consider, so this pseudo expectation allows to correctly characterize games for which we have a first order SOS decomposition in which the polynomials of the SOS can be written in this way, where we just have one Alice observables minus some sum of Bob observables. Then in the SOS decomposition, we're just going to have PI dagger PI. So the only terms where we're going to have two A's are just going to be the two A's which have the same label, right? So that's why we don't even care when we have two A observables with different labels, because we don't consider those games. And then for these games, we could prove this lemma, which was kind of the difficult part to prove, that the expectation value of this PI dagger PI can be proven to always be negligibly close up to a negligible function in the security parameter of the scheme to something which is positive. Okay? Because this is not given for granted anymore. Before we were taking just the bracket of some square of polynomials that was positive by definition, but here this map, it's in principle very weird. So we needed to prove, like here it's where like the cryptographical tools all have to enter. Good. So then going back again to the application of the map to the SOS decomposition, we've proven that we have this kind of structure in which we can see that these values are positive up to a negligible function in the security parameter. And this is good enough because then now we can say that the compiled value of the game is always bounded by the Pearson bound of the nonlocal game plus some negligible function of coming from the encryption scheme. And again, we can do this for games for which we have a first order SOS decomposition with the suitable structure that I described before. Why this is good enough? Because this is actually allowing us to describe already a very broad class of games, which are all XOR games. So, you know, XOR games are those games in which we just have binary outputs. Inputs can be completely uncharacterized. These CHSH games here, elegant spelling inequalities here, and a lot of the inequalities that we use more often to do self-testing are entering in this class of games. Why is it so? Because we know very well how to characterize them. First of all, we can always fix the dimension of the Hilbert space to be equal to 2, thanks to Jordan lemma. So this is a very big advantage for this kind of games. We also have some results that prove that the maximal states that maximize this kind of games always are maximal entangled state. So this is giving a lot of structure, a lot of symmetry in this kind of games. And this is why we know so much about those guys. And this is also what allowed us to prove that for every XOR game, we can have a SOS decomposition of the structure that I described before. Basically, the idea is that even if the structure in the literature is having some sums of A's minus some sums of B's, using the fact that the optimal strategy is always involving these maximal entangled pairs, then we can always do some mapping to basically tweak the SOS decomposition and to achieve this very symmetric structure. But yeah, again, if you want more details, I would suggest to read the papers. And then we also give an example of a higher dimensional inequality. So we fixed this D-CHSH, a generalization to higher dimension of CHSH inequality. We chose it just because we knew that the SOS decomposition was in the suitable form that was working with our framework. And this allows us to generalize the framework to generalize the observables. So very good. So this is kind of the first big result that we had to prove the preservation of these quantum bounds for this set of games. Another thing that we were mostly interested in are these compiled self-tests. So proving that the quantum bound is preserved, it's not enough to prove that the self-testing procedure is also preserved, right? Because in principle, it could happen that in the compiled game, there are different optimal strategies that are not mapped to another. We just proved that the bound is the same, but in principle, I mean, self-testing, it's really relying on the fact that there's a unique strategy achieving that bound. So we need to prove it again. And again, how we do it is that we usually take this SOS decomposition. We know that the polynomials act as nullifier on the optimal state, and this is sometimes good to give us a self-test. So we wanted to see, okay, when we take a self-test statement of this shape, can we translate it to our game? Well, no, not that easily, because the problem here is that when we reach the quantum bound of these compiled games, then we can only know that the sum of this sums is going to be equal to 0. But now there's a little technicality. So it's actually happening the same here in the SOS decomposition, where we have I mean, here it's easier because here, if we have this, since all of the members here are positive, we can automatically deduce that this is true for every I, right? The technicality here is that we don't know that they are positive. We just know that they are negligibly close to something which is positive. So we cannot assume automatically that the expectation value is equal to 0. It could be that something is like a plus epsilon and something is minus epsilon. So what we need to do, we need to use robust self-testing statements. Robust self-testing, it means that when we reach a value in the local game, which is epsilon close to the quantum bound, to the Pearson bound, then we can characterize the optimal strategy to be close enough to the, we can characterize the self-tested strategy to be close enough to the optimal one, right? So there's a lot of technicalities that enter here because we need to define all of the suitable distances and what does it mean to be close enough to something. But yeah, the idea is that here we make this self-test with these statements robust, and then we can have robust self-testing. And this is helpful because then introducing this epsilon, we can indeed prove that the absolute value of these guys, it's going to be bounded by an epsilon coming from the fact that we didn't reach completely the value inequality, and also some function which is again coming from the cryptographic tools. And this, it's allowing us to have self-testing statement. So to sum up, we can only, we can translate self-testing statements, but just if we have robust statements in the non-local side, and we can only self-test what's happening in this second part of the single prover. So for binary observables, it's fairly easy to do. So for all XOR games, we know how to do it very well. We know that reaching a bound which is close to the compiled bound, it's allowing us to bound in the compiled game all of the anti-commutators of Bob's observable to be equal to some, to be close enough to some ideal value. And since for binary observables, we can always fix the dimension of the hyperspace to be true, then if we have a set of measurements and we characterize all of the anti-commutators between all of these measurements, well, this is enough to have a rigid self-test statement. So we provided some examples of useful self-testing which are coming from this result over here. We can, for example, self-test any pair of binary measurements with whichever angle, and triplet of qubit mutually unbiased base measurements doing the compilation of elegant Bell inequality, and so on. So so I reached the end. To have an outlook of the result. So we again studied what was happening in this compilation procedure proposed by Kalai and collaborators. We were able to prove that the quantum bound is preserved in some specific classes of games for which we could find a suitable SOS decomposition, and we could even translate some of the self-testing protocols, so that now we have compiled self-testing protocols in which we just need a classical communication with a central node. There are still a lot of open problems. There's still a lot of open problems that are open in this kind of field. So first of all, we ideally would like to see how much we can push this cryptographic SOS decomposition scheme. Can we characterize better the value of two different Alice observable? That would be very helpful to go to higher order of the SOS decomposition and to describe broader classes of games. Another interesting question is also what can we do in the multipartite case? So I forgot to say that the Kalai protocol that I described at the beginning, it's actually mapping any K non-local prover games to a single prover game where we just need to encrypt the first K-1 round. So, and this is still, they could still prove that the classical bound is preserved in those cases, but they couldn't characterize the quantum bound. So it would be very interesting to, for example, start to see what's happening if we have three provers, how much the quantum single prover is going to be powerful in this case. And then there would be the full generalization. So there would be, which is kind of what everybody's aiming for, to be able to prove that this single prover, this quantum single prover, is not able to win with a probability which is higher than negligible, the Pearson bound of the non-local game. Everybody is convinced that this is true. Everybody is convinced that this protocol is somehow strong enough to constrain the single prover not to win more than the non-local counterparties. But yeah, it seems very difficult to prove it in a very general way. To prove it in a very general way, we cannot use SOS decomposition because we don't have an SOS decomposition for every Bell inequality. So we should do something which is more fundamental and like try to really try to characterize a bit better what's happening in the quantum prover. And that's it.